In short rate models, we specify the dynamics of the short rates. In the HJM framework, we take a different approach. We specify the evolution of the entire forward curve directly. As a consequence, the initial forward curve enters as an exogenous parameter. So there are no tiers with fitting the initial forward curve as we had them with the short rate models. We will see that the drift of the forward rate dynamics is going to be fully determined by the volatility of the forward rate dynamics. This is the famous HJM drift condition. The HJM framework is very broad and it contains all interest rate models which are driven by a finite number of Brownian motions. Formally, as ingredients, again, we fix a filtered probability space, which is now carrying a d-dimensional Brownian motion. A d-dimensional Brownian motion is simply composed of independent standard scalar Brownian motions, W1 to WD. In turn, we need d market prices of risks that we stack into the d-dimensional market price of risk vector lambda, and the Giordano theorem still applies under the risk-neutral measure Q, which is equivalent to P with the radon-Nikodym density process as given here. Under this measure, the process W star, which is the Brownian motion under P plus the market price of risk drift, is a Brownian motion under Q. The HJM framework, or HJM framework, is very broad and contains all interest rate models driven by a finite number of Brownian motions. We specify directly the evolution under Q of the entire forward curve. Formally, this means for every maturity capital T, we let the forward rate process as a process in small t follow an Ito process with drift alpha and volatility sigma, which are both indexed by the maturity capital T, but otherwise are processes in small t as we are used to in the case of generic Ito processes. We will see later on that the drift process alpha is going to be fully determined by sigma. That is going to be a consequence of the arbitrage pricing theorem. Keep in mind that sigma is now a vector-valued process. We stack the d component sigma 1 up to sigma d into this row vector that we call sigma. We are also given as an exogenous parameter an initial forward curve, F0 capital T. Bond prices are explicit in terms of the forward curve. This is in contrast to the short rate models, where bond prices were given implicit in terms of the integrated short rates via a conditional expectation under the risk-neutral measure. Hence, in contrast to short rate models, here we can directly infer the dynamics of the bond prices in terms of the dynamics of the forward rates by using Ito's formula. Let's do this in several steps. We first start with the process that is in the exponent of the right-hand side. We see that running time small t is showing up at two places as an integration boundary and the time argument of the forward rate process. Formally differentiating under the integral sign gives us the integrand at the lower integration boundary f small t, which by the way is just the short rate rt, as we are going to write here, minus the integral of the differential of the integrand. We then plug in the differential of the forward rates and change the order of integration, dt du, and the same with dw star t du, and we arrive at the second line here, where we use shorthand notation and define VTT as minus the integrated forward rate volatility. Summarizing this first step, we have shown that the T-bond price is given by the exponential of an Ito process whose decomposition is given here. We can now apply the Ito formula. The Ito formula applied to the exponential function gives us what we see here on the first line. Notice that I have divided on both sides by the T-bond price. Plugging in the expression for the Ito decomposition of this process here from the previous slide, we arrive at what is shown here. This is the T-bond return decomposition into drift component and martingale component. From the arbitrage pricing theorem, we know that the expected rate of return, the drift of the T-bond under the measure Q, has to be equal to the short rate. But this implies that minus the integral of alpha du plus 1/2 squared norm of V has to be 0. This must be true for all maturities capital T. So if we differentiate this equality in capital T, we arrive at this HJM drift condition. The drift of the forward rate dynamics, alpha, is fully determined in terms of the forward rate volatility sigma. Summarizing, we arrive at this HJM theorem. The Q dynamics of the forward rates is fully determined by the forward rate volatility sigma because the drift that we use to label alpha is given in terms of sigma as shown here. The corresponding risk-neutral bond price return dynamics is of this form. It has a risk-free expected rate of return and a volatility V, which again is defined as minus the integrated forward rate volatility. The minus sign comes from the fact that an upward shock in the Brownian motion W star drives forward rates up. Rates going up means bond prices go down. The HJM framework contains all the short rate models we have seen so far. So which HJM model, sigma TT, corresponds to the Vasicek short rate model? To answer this question, we recap the Vasicek short rate model dynamics, and we recall that the Vasicek short rate model implies forward rates, which are affine functions in the prevailing short rate. The functions a and b are given in closed form. They solve a system of Riccati equations. The first order derivative of b is e to the minus kappa cap t minus small t. This is enough, applying integration by parts, to determine the martingale component of the forward rate dynamics, which is as shown here. We could as well, by integrating by parts, by apply stochastic calculus, derive the drift of this implied forward rate dynamics. But we don't need to go through these calculations because the HJM theorem already tells us what the HJM drift here has to look like. It is given explicitly in terms of the volatility of the forward rates.